welcome back everyone to our seminar. And today, Prem is going to talk about quantum automorphism groups of trees.
Hi everyone, I'm Prem. I'm a PhD student at DTU, and today I'll be presenting joint work with these people. Hopefully I'm audible and you can see my screen. So yeah, I'll be talking about quantum automorphism groups of trees. So so things to characterize symmetries of trees can be traced back to Jordan and Polya, and these are like really ancient papers. But it is a well-known result in graph theory that the automorphism groups of all trees can be constructed from the trivial group by taking iterated direct products and Rath products with the symmetric group, the complete symmetric group, Sm. It is also known that but no similar result is known for quantum automorphism groups of graphs. As a matter of fact, not a lot is known about quantum automorphism groups of graphs. The explicit quantum automorphism group of very few graphs is known, and there's definitely no such characterization of such a large family of graphs, and this is one of the first such characterization. And what makes this particularly interesting is that it is known that almost all graphs do not have quantum symmetry. We will see what that precisely means in a while, but almost all trees do have quantum symmetry. So, and in what follows, we will see a quantum analog of Schroeder's theorem, and the main idea of the proof is similar to the classical proof. I will not be presenting the classical proof because the idea is like way too similar to the proof we're presenting. And I'm sure that once you see the proof of the one that we are doing, you will also be able to figure out roughly how to do the classical proof. Right, so first we'll start with some definitions and some background, and then we will proceed on our results. Right, so the quantum automorphism group of a graph, which is of a graph G, which we denote by QG. We define it to be the universal C-star algebra, C of QG, which is generated by elements Uij, where I and J are from the vertex set. So these Uijs, they need to be self-adjoint projections. And if you take the column sum, if you add over the outputs J, if you add over the vertices J, or if you add over vertices I while keeping the other one constant, then you get 1. And it additionally needs to satisfy that this, if you take this matrix U and you multiply it with the adjacency matrix of the graph G, then it needs to commute with the adjacency matrix of the graph G. And this is sort of like a generalization of the fact that if you have an automorphism of a graph, then that if you take it as a permutation matrix, then it commutes with the adjacency matrix of the graph. And you also have this comultiplication map, which is not really important for the purposes of this talk. But yeah, this is like the analog of the classical multiplication. So if you have a group, then you can multiply 2 elements, and this is sort of the analog of that. And this matrix Uij is what we will be primarily concerned with. And this matrix Uij is known as the fundamental representation of this group. And a matrix Uij that satisfies these first 2 conditions is known as a magic unitary. So if each of the entries of the matrix is a self-adjoint projection, and if the row sum and the column sum is 1, then you call it a magic unitary, and it's sort of like a non-commutative analog of a permutation matrix or a doubly stochastic matrix. And we also need the quantum automorphism group of a vertex-colored graph. So it is the quantum automorphism group of a vertex-colored graph is, so you first consider, you take the C-star algebra, you consider the C-star algebra with respect to this uncolored graph, and then you quotient it by this additional relation that Uij is 0 if C of I is not equal to C of J. So this entry corresponding to Ij, where I and J have different colors, it needs to be 0. And it should be a vertex-colored graph, but yeah, a graph is said to have quantum symmetry if the C-star algebra that's generated is non-commutative. And it is known that if the C-star algebra is commutative, then the C-star algebra is the set of all continuous functions on the automorphism group of the graph. So in this case, we say that the graph has no quantum symmetries because it doesn't have any like non-trivial quantum symmetries. A rooted tree is a tree with one of its vertices R, which is identified as a root. And the root has its own color, and all the other vertices have a different color, and all the other vertices are in the same color. And we shall denote the quantum automorphism group of a rooted tree when it is viewed as a colored graph as qt R of t. And note that whenever we are taking the quantum automorphism group of a colored graph, we will write qt C of t. Another closely related notion that is like to these quantum automorphism groups is that of quantum isomorphism that is introduced in this paper. So two graphs G and H are said to be quantum isomorphic if there is a non-unital C-star algebra A and a magic unitary U X Y such that AGU is UAH. So you need this magic unitary to commute with so when you to sort of commute with the adjacency matrices, and we can again see that this is like a non-commutative generalization of the fact that if you have an isomorphism between two graphs, then if you express this isomorphism as a permutation matrix, then it commutes with it sort of conjugates with the adjacency matrices of these two graphs. And additionally, you require that uxy is 0 if c of x is not equal to c of y. So basically, you're not allowed to send a vertex of one color to a vertex of a different color. So now we will define what are called quantum orbits and quantum orbitals. So let C of q, g, comma u be a quantum automorphism group of a graph G. So we have the following relations that we can define. So for I comma j belonging to the vertex set, we define I related to j if uij is not 0. And similarly for ij and kl, we define ij related to kl if uik times ujl is not equal to 0. The second one is slightly weird, so maybe I'll just reiterate this. Ij is related to kl if uik ujl is not equal to 0. It was also shown that these relations are equivalent relations, and the partitions of the vertex set of G induced by this relation tilde 1 are called the orbits of this quantum automorphism group to G, and the partitions of V of G cross V of G induced by tilde 2 are known as the orbitals of QG. And now we will speak a little about color refinement because it is useful, to prove something. The color refinement algorithm, we start by labeling each vertex of a graph in its actual color. Then we update the color of each vertex to the multi-set of colors of the neighbors of that vertex. And we keep doing this till it stabilizes. And this always eventually stabilizes, and this stable partition is the output of the algorithm. And we know from this paper by Lupini, Manchinska, and Robertson that whenever you have okay, so this result follows from their results, but it wasn't explicitly written down. So we were the first to explicitly write this down. So if you have, so this basically says that if vertices end up with the different colors, and they are in different quantum, they are in different orbits of the quantum automorphism group. In other words, the output of the color refinement is a graining of the orbits of the quantum automorphism group of G. Color refinement, well, the initial idea was to use it as an isomorphism test. So given two graphs G and H, we can run color refinement on their disjoint union. And if the resulting partition has one part that contains a different number of vertices from G and H, then we can conclude that G and H are not isomorphic. However, note that the converse is not true. In fact, it is known that all of the resulting partitions have the same number of vertices from G and H. if and only if G and H are fractionally isomorphic. So it's possible that G and H are not isomorphic, and still you can end up with the same with them having the same number of vertices in each one of these partitions. In again this paper by Levine, Munchen, and Robertson, it was shown that two graphs are quantum isomorphic. If they're quantum isomorphic, then they're fractionally isomorphic. Additionally, it is known for trees that they are fractionally isomorphic if and only if they are isomorphic. And this allows us to say that if you have two trees, if you have two trees, then they're quantum isomorphic if and only if they're isomorphic. Because so if two trees are isomorphic, then they are trivially quantum isomorphic. And if they are quantum isomorphic, then they would be non-signaling isomorphic. And if they're non-signaling isomorphic, then it follows from what we just previously saw that they would be isomorphic. And this allows us to prevent some tricky situations, such as the quantum automorphism group of a disjoint union of two graphs which are quantum isomorphic but not isomorphic. And yeah, this lets us avoid that tricky situation. So we now give a list of operations that do not change the quantum automorphism group of a graph. We will omit the exact proofs of these statements. Okay. So first we say that if subset of vertex set of X is an independent set that is a union of color classes, then adding so let's choose two vertices, one for each distinct pair of vertices in S, does not change the automorphism group. Okay, so that is very difficult to understand. So maybe this picture will help us out. So this is an independent set. There is a union of color classes. So if you see that this pink color doesn't appear elsewhere, this blue color doesn't appear elsewhere, and F is an independent set, then if we make S into a complete graph now, then that doesn't change the quantum automorphism group of the graph. Similarly, if S and T are defined sets such that S union T is an independent set, and each of S and T is a union of color classes, then if we add this complete bipartite graph between S and T, then this doesn't change the quantum automorphism group. Again, so if you look at S and T, they are unions of color classes. The colors that are in S and T, they do not appear elsewhere. And if you add this complete bipartite graph between S and T, then that doesn't change the quantum automorphism group. Similarly, again, if S is a monochromatic vertex set, there's a union of quantum orbits of X, and then changing the color of S to a new color that doesn't occur elsewhere in the graph doesn't change the quantum automorphism group of the graph. So again, so you see this green. So this is probably not actually a union of quantum orbits, but let's say it is. If you see this is a monochromatic vertex set, this color green can appear elsewhere, but within the vertex, all of them need to be the same color. And if we change them from green to pink, then that would not change the quantum automorphism group. And lastly, if you just add an isolated vertex in a new color that doesn't occur elsewhere, then this doesn't change the quantum automorphism group. So if you have this some graph, if you just add a new vertex, it's an isolated vertex, and it's just it's in a different color. This color shouldn't be anywhere else in the graph. Then this doesn't change the quantum automorphism group. The proofs follow mostly through some algebraic manipulation of these fundamental representations. But yeah, we will. So most of the proofs that we will see in this talk will be using these things as building blocks. Right. So now we will define what we call the rootification process. So by applying the previous modifications, we can transform any given tree E into a rooted tree R, such that the quantum automorphism group of the rooted tree is the same as the quantum automorphism group of the tree. So before we look at how exactly we do this, first we should note that the center of a tree is the union of quantum orbits. Okay, so it is the Jordan center of a tree can be found by iteratively removing the leaves of the tree. So you remove the leaf at first, then you're left with the subgraph, and then you remove the leaves from that subgraph, and you keep repeating this process. And it's known that the leaves of a tree are a union of quantum orbits. Each time you remove the leaves, the graph that you're left with in itself is a union of quantum orbits. So that allows you to conclude that the Jordan center itself is a union of quantum orbits. And it's also known that the Jordan center for a tree, it's either an edge, so it's a pair of vertices that are connected, or it's just a single vertex. So we take the case where the Jordan center is a vertex, and this case is very simple. So let's say this is the sorry, I forgot to apologize about the diagrams. The drawings are probably not great, but hopefully they capture the essence of the idea that I'm trying to convey. Okay, so yeah. So if this is the Jordan center, and let's say these are some subtrees, then in order to turn this into a rooted tree, we just color the Jordan center in a different color, and this gives us a rooted tree that has the same quantum automorphism group as the previous tree. Now the case is slightly tricky. By the way, we can do this by using property 3, because this is, if you see here, then the Jordan center is a monochromatic vertex set that is a union of quantum orbits. So we are using the construction number 3 from the previous 4 constructions that we saw. Okay, so now if the Jordan center is an edge, then again by using property 3, I can color these vertices in a different color, pink. Then I can remove the edge between these 2 pink vertices by using property 1. I can add this isolated green vertex by using property 4, and I can add these 2 edges. Yeah.
What is your quantum automorphism group of the tree?
I'm sorry, I could not hear the first part.
Okay. In the root of the tree should not change the quantum automorphism group of the tree, right?
Yeah, I'm sorry. Could you please repeat?
Because you were just constructing. Sorry, you were constructing the rooted tree, right? And then saying that rooted tree has the same quantum automorphism group of the as the original, but changing the root of the tree doesn't really change the quantum automorphism group, or does it?
Oh, yes, you're right. The root is by it's fixed by automorphisms. We know that, but it's also fixed by quantum automorphisms, because if you have a single vertex, then it's a quantum orbit in itself. So that vertex, a quantum automorphism cannot take that vertex elsewhere. So yes, you're right, and that is precisely what we are doing here. But here we just want it in such a way that we only have one Jordan center, but here we have 2. So we'll just be subdividing this edge, and we are just making sure that the quantum automorphism group does not change. We're just being pedantic about it.
Okay, thank you.
Right. So as I said here, since this Jordan center is a union of quantum orbits, I can change the color of these things to pink. Then I can remove the edge using property 2. I can add this using property 1. I can add this isolated edge in green using property 4, and then I can construct this, which is a complete bipartite graph using property 2. And then again, since these 2 pink things are a union of quantum orbits, I can color them back to black using property 3. Actually, property 3 allows us to go from here to here rather than from here to here. But yeah, it doesn't change the quantum automorphism. That is what we should keep in mind. Similarly, we can do a derootification process. That is, for each rooted tree, we can construct an unrooted tree. We can just construct a normal tree such that the quantum automorphism group of this rooted tree is the same as the quantum automorphism group of the tree. I will some of the details for this construction, but it's sort of similar to what we did previously. It would follow from the four rules that I described earlier. So what we essentially do here is that attach a really long path to this root in such a way that the Jordan center of this new graph, it should fall somewhere on the path itself. And we can show that the quantum automorphism group of this tree is equal to the quantum automorphism group of this rooted tree. Okay. Now we will describe a couple of concepts from quantum automorphism groups that can be thought of as direct analogs of the direct product of groups and taking the Ret product with a group. So if C of Q GU and C of Q HV are the quantum automorphism groups of two graphs, their direct product is defined as the quantum permutation group, as this group, where the C star algebra is what is known as the free product of the C star algebras of these two quantum groups, and the magic unitary is the direct sum of the magic unitaries of these two things. It is known that if B and H are two graphs that are not quantum isomorphic, then the quantum automorphism group of the disjoint union of these two things will be the free product of the quantum automorphism groups of the individual graphs. And this can be strengthened to the following. So if you have a vertex colored, let X be a vertex colored graph with connected components X1, Xn. If, okay. I have unfortunately the wrong result here, but maybe I'll just explain the result. So if you have a quantum automorphism, if you have a graph, there is a disjoint union of subgraphs which are not pairwise quantum isomorphic. Then the quantum automorphism group of this disjoint union is the free product of the quantum automorphism groups of the individual graphs. I'm sorry, this is a lemma that we use to prove that theorem. Unfortunately, I have forgotten to attach that result. I'm sorry. So I will just reiterate it just one more time so that it's clear. So if you have a graph that is a disjoint union of a bunch of graphs that are not pairwise quantum isomorphic, then the quantum automorphism group of this disjoint union is the free product of the quantum automorphism groups of these individual graphs. And maybe we should just note that here our condition is that these graphs are not quantum isomorphic, not that they're not isomorphic, right? And there is one intermediate, so we know what to do when these graphs are isomorphic as well. We'll see in a while. But as I said a while earlier, the intermediate case that when these graphs are quantum isomorphic but not isomorphic, so we do not know what the quantum automorphism group of the disjoint union is, and that is maybe an interesting problem, at least to me. Okay, so we have seen what to do, how to take the disjoint union of how to compute the quantum automorphism group of the disjoint union of some graphs that are not quantum isomorphic. But when you just take the disjoint union of multiple copies of a connected graph, then you have this this theorem. So if you have a connected vertex colored graph, and if you take a disjoint union of just n copies of it, then the quantum automorphism group of this disjoint union can be described by what is known as the free Ret product of this quantum automorphism group of these individual graphs with this group Sn plus, where Sn plus is the quantum automorphism group of the complete graph on n vertices, or the empty graph on n vertices, whichever you find more comfortable. And yeah, now we introduce the last that we need to prove our theorem, and then we will look at our result. So if F is a forest of rooted trees, and f tilde, let f tilde be the rooted tree obtained by deleting the root, and then let f tilde be the rooted tree obtained by connecting the roots of the individual trees of f to a single new root. Then the quantum automorphism group of this forest of rooted trees is isomorphic to the quantum automorphism group of the rooted tree we had earlier. So if you have a bunch of rooted trees like this, and we are assuming that their roots have the same color, then what you can do is that since these have the same color, they will be a union of orbits. There will be a union of orbits, and that's okay. First of all, you can just add a isolated vertex in green. These are a union of, and then you can add these. This complete bipartite graph by property 2, and even after this, they remain a union of quantum orbits, so you can just change their color to black. And this allows us, so whenever you have like a forest of rooted trees, you can use this to construct a rooted tree such that the quantum automorphism group of that disjoint union of that forest is the quantum automorphism group of this rooted tree. So we did all of this stuff about rooted trees. So of course we will be focusing on rooted trees. So this is the statement of our result. Class C of all the quantum automorphism groups of all trees can be constructed inductively from this group 1, which can be thought of as the quantum automorphism group of the tree with a single vertex and no edges, so just a dot. And so if G and H are in this class, then the free product of them is in this class. And if G is in this class, then the free earth product of G with this group Sn plus is also in this class. And of course, since we did all of this stuff about rooted trees, we will be reducing our theorem to rooted trees. So since given any tree, we can construct a rooted tree that has the same quantum automorphism group, and we can do the vice versa. So we can just focus on rooted trees because they are much easier to work with. So it's very easy to see that this trivial group is in the class, of course. Now assume that you have some groups G and H that are in the class. Okay, there should be a math-cal T, sorry. Then you can construct rooted trees. Since these are in this class, there are rooted trees G and H, such that quantum automorphism group of G is this math BBG, and quantum automorphism group of H is this math BBH. So now we claim that the G star H is the quantum automorphism group of the rooted tree that we construct as follows. So what we do is that we take G, we take H, and we add a green vertex, and we just use this theorem that so we are just using the theorem that we saw about these rooted forests. So if you just had the disjoint union of G and H, then the quantum automorphism group of the disjoint union, it would be the free product of the individual quantum groups. So it would be, in particular, it would be math BBG star math BBH, and we use this forest to trees construction. And this tree now has quantum automorphism group math BBG star math BBH. And on the other hand, so note that here we only did it when G and H are not isomorphic. So when G and H are isomorphic, then your trees G and H also become isomorphic. So if you take their disjoint union, then the quantum automorphism group of that, it is the free earth product. It's no longer the free product. So you have to do some slight manipulation, right? So if you have some G belongs to tau, then there is a rooted tree G, such that quantum automorphism group of G is math BBG. Then math BBG star math BBG is the quantum automorphism group of the rooted tree that we construct as follows. So first, we use rooted trees to forest lemma, and we just attach an extra node to this, and that does not change the quantum automorphism group of this tree. And these two trees now have a different number of vertices. They cannot be quantum isomorphic. So but they have the same quantum automorphism group G. So when we take the disjoint union, then the quantum automorphism group of the disjoint union is math PBG star math PBG. So and then we use the forest to trees construction to conclude that the quantum automorphism group of this rooted tree is math PBG star math PBG. And now we are just left with one case where we have to say that if math PBG is in the class and math PBG free Reth product Sn plus is in the class, and so we just take n copies of. So let's say the quantum automorphism group of G is math PBG, and we just take n copies of G. I know these don't look like n copies of the same graph, but so yeah, and then you can again use this forest to trees construction, and the fact that whenever you have like a disjoint union of n copies of a graph, the quantum automorphism group of that disjoint union is the quantum automorphism group, or is the free Reth product of the quantum automorphism group of G with Sn plus, to conclude that the quantum automorphism group of this tree is math PBG free Reth product with Sn plus. So we have now shown that we have shown inclusion in one direction. Now we need to show inclusion in the other direction. So in particular, we need to say that for any rooted tree, its quantum automorphism group can be constructed by using the free Reth product and free Reth product with Sn plus and free products iteratively, and just using the trivial quantum automorphism group. Okay, so let T be this rooted tree, and let T tilde now be the forest of rooted trees that is constructed by deleting the root of T and designating the neighbors of T as the roots of the trees that are formed. So if you just remove the root, then you get a bunch of subtrees, and so the vertices that were the neighbors of the root we now designate as the roots of these new trees that are formed. And of course, we know that we know from this forest to rooted trees lemma that the quantum automorphism group of T is the same as the quantum automorphism group of T tilde. And then we use the result that we had about these disjoint unions of graphs to say that if we so this T tilde will now consist a bunch of trees. Some of them will be isomorphic and some of them will be not. So let's say we just divide them up into classes. So you just group together the ones that are isomorphic, right? So let's say you have mi copies of the rooted tree Ti. Then you can say that the quantum automorphism group of T tilde is equal to the quantum automorphism group of the rooted tree T. It is the free product of this quantum group, which is the free Reth product of the quantum automorphism group of Ti with Smi plus, right? And now you end up with these subtrees that you get from deleting the root. And now you just iteratively apply this construction over and over to these rooted trees, and eventually you will end up with trees that only have one vertex and no edges. And this tells us that we can construct the quantum automorphism group of this rooted tree by iteratively using 1, 2, 3. I wanted to do an example, but unfortunately couldn't make the slides for that. But we should note that this actually gives us like an algorithm to actually do this, because you can just remove the root iteratively, and eventually you will end up with trivial, with just trees with just a single vertex and no edges, and we know what and so this gives us a algorithm to actually calculate the quantum automorphism group of these trees. Yeah, that is all I had prepared. So thank you very much.
Thank you very much. Any questions for Prem? Okay, so just one quick question.
Yeah.
So does it imply that all trees have quantum automorphisms?
No, that is not true. So if you have just if you just have like a cherry, just one vertex, and so that has no quantum automorphism. So it is not. So this paper that I was talking about a while earlier, that all trees have quantum symmetry, that says that if a tree has two cherries, then it has quantum symmetry. And
Sorry, could you repeat that?
if a tree has two cherries,
Two
so
roots?
no, so two vertices that are like, so if your cherry is one vertex attached to two leaves.
Oh yeah.
So if you have two of these things, then you have quantum symmetry. And
Yeah, this is Schmidt's result. Yeah.
but it's not true that all trees have quantum symmetry.
Right. So what are there any other conditions that will guarantee, because you have this construction for the quantum automorphism group, right?
Yes.
So do you have any necessary conditions for sufficient conditions for the tree to have the
Yes, so we can say that essentially we can say that if you have S2 free product S2 somewhere, S2 plus free product S2, then you have quantum symmetry. Or if you have S4 plus somewhere, then you have S4 or S5 plus. So any Sn plus where n is greater than 4, then you have quantum symmetry. And that seems to be the case only when a tree has two cherries, but
Oh really?
I'm not sure. I'm not sure. This is something I'm saying. I'm not
Okay,
sure.
that's interesting. Well, it probably generalizes to more than just two cherries, right? So if you have just two paths that come from the same, that's like a big cherry. Okay. Okay. Interesting. Yeah. Thank you. So Ada had a question.
Yeah. So this is the first time I see the colored version of quantum symmetry. So I have some really basic question. So is it possible for a graph to have, say, two different coloring but different quantum symmetry group? Or in particular, is it possible for a graph to have two different coloring where one, if you look at the UIJs, they all commute, and then a different coloring where the UIJs could be non-commutative?
I don't have any examples of the top of my head, but I think that should be doable. Yeah, I definitely think it should be possible. And yes, so we are just taking, so when let's say you have some uncolored graph and when you have some coloring, so what you get is like a quotient of the C-star algebra, and you can take quotients in such a way that the C-star algebra becomes commutative. And other quotients can still be non-commutative.
So is it anything special if you take a proper vertex coloring of the graph?
I'm sorry?
Like if you take a proper vertex coloring of the graph, would you get anything special about the quantum symmetry group?
Yeah, I do not know. I haven't thought about it, and I do not know.
Thank you. Yeah.
But probably if
as a very basic example, if you have Kn, complete graph, with all vertices in the same color, then the quantum automorphism group is going to be Sn plus, so this free symmetric group. And if you take a proper vertex coloring, so all vertices have different colors, then the requirement is actually that the quantum automorphisms must preserve the colors, so you're only going to get the trivial quantum automorphism. And in particular, then that's classical, so all entries commute.
Yes.
Okay. Thank you.
Bill?
So I don't know if this is a fair question. I assume that the class of quantum groups that you're building here are fairly specialized. Is there a way to sort of indicate to us how unusual these groups are relative to other quantum groups, or do you think that that the quantum groups for graphs on n vertices might generally resemble the ones that you've found? I mean, these Rietz products of symmetric groups tend to be very, very special. Is there some easy way to convince me that these are very unusual or very rare groups?
Yeah, I unfortunately do not have an answer for that right now, but I think that's an interesting thing to think about. But yeah, and
Classical analog, one would assume that a Reith product with symmetric groups doesn't happen very often for graphs, but I don't know anything about quantum groups, so I don't know how common it would be to have a group in this family as the automorphism group of a graph.
yes.
Thank you for the very nice talk.
Thank you very much.